So I'm going to talk about an LP-based approximation algorithm for personalized reserve prices. This is a joint work with Negin, Golrezaei, and Renato, Paes. So we have a second price auction, and we are allowed to set different reserve prices for different buyers. And we want to maximize the revenue. The main motivation behind our work is for display advertising market, where they want to run auctions to sell ad views. For example, here we have this ad slot. When a user visits this website, they run an auction, usually a second price auction, to sell this. So they get the bids, decide which ad to show, and what the payment is. It's been shown that to earn high revenue, setting right reserve prices is crucial. Okay, why do we want to use reserve prices? Why are they important? Why are they widely used? We know that in the celebrated work by Meyerson, it describes the optimal auction under some assumptions. For example, if bids come from regular and distributions, second price auction with the reserve price is optimal. However, if these distributions are independent but non-identical, optimal auction needs to compute virtual values for each buyer, which is complicated to implement in practice. And even if we manage to do that, we'll still prefer simple mechanisms to reduce the risks introduced by assumptions of the model. And in many real cases, bids are not even independent. So we need simple mechanisms that are truthful, such as second price auction. Now we would like to add reserve prices to second price, personalized reserve prices to second price auction. Since empirical and theoretical evidence highlight the significance of using them. There are different ways to apply personalized reserve prices. One is eager and the other one is lazy. It's been shown that eager is superior to lazy, so we'll just focus on eager. In this auction, given a vector of reserve prices R and a vector of bids, we will first discard the bids that do not meet the reserves, meaning that the reserve is greater than the bid. Then winner would be the buyer with the highest bid amongst the remainings. And their payment would be maximum of the second highest bid amongst the remainings and reserve of the winner. Here, for example, we have these bids, and if we want to apply this vector of reserve prices, we would have to first remove these bids that are smaller than reserves. Then winner would be buyer 2, and their payment would be maximum of the reserve and the second highest bid. So there are different settings in which we can consider this problem. The first one is Bayesian optimization. We assume that we are given buyers' valuations distributions, and we want to maximize the revenue. The second one is online optimization. We assume that we can set different reserve prices at each time, and we just want to minimize the regret. The last one, which is the one we consider, is offline optimization. We assume that we are given submitted bids over n different auctions, and we want to maximize the total revenue across them. So why do we choose offline optimization? Compared to Bayesian, for Bayesian optimization, we need to have the buyer's valuation distributions, and we need to estimate them. This process is sensitive, and also we get that from data set of auctions. So why not just use them directly and run an offline optimization algorithm? And compared to online, as I mentioned, the application of our work is in display ads auctions, which is a real-time auction. And we have millions of them in each second, and we only have a millisecond to respond to them. So we cannot run algorithms with heavy computation in each round. Also, because of huge volume of data that we have, we can run offline optimization that have good performance. So we also know that any alpha approximation for offline optimization gives almost the same approximation for Bayesian setting by Morgenstern and Derakhshan. So this is a plus for our work. Now I just state the problem more formally. We have a single item to sell and a set B of n buyers that are participating in our auction. And our input is submitted bids to a set of auctions A. We have beta of B and A, which is bid of buyer B in auction A. And our goal is to find a vector of reserve prices that maximizes the revenue across all the auctions. Revenue would be the sum of revenue obtained from each auction, which is auction. As an example, we have 4 buyers and their bids in 4 different auctions. If we want to apply this vector of reserve prices, we'd have to first remove the bids that do not clear their reserves, pick the winners, who have the highest bids, and the revenue would be in each auction, the revenue would be the maximum of the reserve of the winner and the second highest bid amongst the remaining. There has been some previous works on this problem. These are the most related ones. The first one is by Paes and Vasilevsky. They give a formal definition of eager and lazy auctions and show that it's NP hard to find the optimal vector of reserve prices. They also give a one-force approximation algorithm for this problem in offline optimization setting. And the second work is by Derakhshan and Bang. They give a one-half approximation for eager in the offline optimization setting and generalize it to get a one-half no-regret online algorithm. They also show that finding the optimal vector of reserve prices is APX hard, which means you cannot hope for getting a p-test. Their work is more broad, but these are the things that are related to ours. So our main result is an algorithm with 0.68 approximation factor, which beats the previous work by one-half approximation. To get that, we first design an integer linear program to describe the optimal solution, then relax the integrality constraints and get a fractional. Then round it to an integral solution, and our output would be the best of this solution and the all zero vector of reserve prices. Using all zero vector of reserve prices means just running a simple second price auction with no reserves. And the revenue of that would be the sum of second highest bids in all auctions. We also show that the integrality gap of our LP is bounded by 0.82, which means you cannot get better than this bound using this LP. Also, we show that our analysis is tight, meaning that using our rounding procedure and this LP, we cannot get better than our approximation factor. And by the result that I mentioned, we can get the same approximation factor for Bayesian optimization. Some of the challenges that we face, let's first talk about what the previous work had. To set the reserve prices, they only use the 2 highest bids in each auction. And to compute that, they compute the reserve price of each buyer in isolation. And Derakhshan and Bang show that this is exactly the reason that they do not get better than one-half approximation. So questions for us here, how to optimize these reserve prices jointly and how to use all of them. So we intend to write an integer linear program, and here are 2 first attempts that failed. The first one is to just use the natural representation of the solution, which would be a vector of reserve prices. But in this case, we'll have exponentially many variables. Okay, M here is the number of auctions. And it's easy to see that reserve price of each buyer would be equal to one of their bids in one of the auctions. So the number of possible solutions would be M to the power of N. And the second one was to have a variable for each buyer and the reserve, and set it to 1 if this buyer has this reserve. But in this case, the objective function is not linear because it consists of several maxes. So to overcome that, we give an alternative representation of the problem space. We have this interesting observation, that is, the revenue can be determined only the following information. we only need to know who has the highest clear bid and what the reserve is, and who is the buyer with the second highest clear bid. So based on this observation, we define a set of valid profiles for each auction, which is a total of 2 buyers and 2 reserves. And it should satisfy that bid of B1 in this auction is greater than bid of B2, and the reserve prices are respectively smaller than the bid of 2 buyers. We want to use this to capture what happens in each auction given a vector of reserve prices. And given this profile, the revenue obtained from that would be maximum of bid of the second buyer and reserve of the first buyer. And notice that we have only polynomially many profiles here. So here is how we use this and write an ILP. We have this variable S of A and P, which would be equal to 1 if and only if the profile P is the case in auction A. What does this mean? It means that the vector of reserve prices that we get in that buyer, like in this auction, in auction A, buyer B1 has the highest clear bid, buyer 2 has the second highest clear bid, and these are their reserves. And also note that here we have revenue obtained from auction A given profile P, and since we have only polynomially many profiles, we can just pre-compute them. It doesn't matter that it's not linear.
Here the result is the same for all auctions. Right?
Yes. In that example,
yeah.
you could see it.
Yeah. But it can also change for different auctions.
No, this is an offline optimization algorithm, so we have to set the same reserves for all the auctions.
But if we change that assumption,
That would be online optimization. That would be online optimization. Okay. So this is our revenue function. And this constraint is to enforce that each auction gets exactly that. Each auction has exactly one profile. We also have the variable which is Q of B and R, and would be equal to 1 if we have assigned reserve R to buyer B. And we want it to be equal to 1 if, because we want to assign exactly one reserve to each buyer. This last constraint is to make sure that we assign exactly one reserve to each buyer, and we do not assign different reserves to the same buyer in different auctions. Okay, is it clear? Okay. So we define this set, which is the set of profiles in auction A that assign reserve R to buyer B. The left-hand side is equal to 1 if we assign reserve R to buyer B in auction A, and it should be less than or equal to Q of B. Okay, so to get our algorithm, we relax the integrality constraints, which mean our variables can be real.
So where do you consider second price induction?
Oh.
LP. Where do you consider?
Oh, it's in the profiles. Because like the revenue of the profiles is computed in a way that, here, let me just. The revenue of each profile is maximum of the reserve of the first buyer and the bid of the second buyer. Okay. Okay, and then we consider Q from the optimal fractional solution. And for each buyer, we choose a reserve price, or we independently with probability proportional to Q of B and R. And then, between this solution that we obtained and the all zero vector of reserve prices, we return best of them. So our analysis of our algorithm is involved, so I'll just give some intuitions about that. The rounding loss of we define the rounding loss of an auction to be the amount of revenue that we lose due to the rounding procedure from auction A. And we bound it as a function of the second highest bid in that auction. And we show that it's C times the second highest bid in that auction, and C is this strange number. And then we can compute the revenue from each action, which would be maximum of this optimal solution of the LP minus the loss, and the revenue obtained from only running a second price action with no reserves. Here, the interesting thing is that we compute the rounding loss as a function of the second prices. So now we can connect these two together and show that this function would give us 0.68 of the optimal solution of the LP, which would also be which would also give us this approx factor of the optimal solution. So you might wonder where that strange number comes from. It comes from this optimization problem, and I'm not going to details of that. We can just take it offline if someone is interested. And in conclusion, we studied the problem of optimizing personalized reserve prices in eager auction, present a novel LP formulation to describe the optimal solution, and round it and get a 0.6 approximation that improves over the 1/2 approximation due to Roughgarden and Wang, and we also bound the integrality gap of the LP and tightness. We give a tightness result. So here are some open problems. It would be interesting to improve the approximation factor of the eager problem in Bayesian setting or in the online setting. In the online setting, it should be 1/2 approximation because our work doesn't give a better approximation for that. And using these ideas to get improved approximation for other actions like boosted second price action. Thank you.